So, good afternoon to everyone. Good afternoon.
Good
So
afternoon,
today,
sir.
yeah, good afternoon. Today we will discuss upon the helical antenna which we have started before. So, as we have discussed in the previous class, helical antenna is a group of, you can see the helix axis is available and you are just rotating the wire and the wire thickness will be D, and one of the helix or one of the rotation you can say that it will be L, and you have spacing between the two helix, that is S, and it can be the number of turns can be N. So these all things we have seen. So D is the diameter of the helix, C is the circumference, and S is the spacing between the turns, alpha is pitch angle, L is the length, and N is the number of turns, axis length, and the diameter of the helix. D, small letter D. So apart from that, we have seen that what does the circumference, diameter, and all free space wavelengths, and the pitch angle, everything we have discussed in the previous class. And along with that, we have also seen that the helix may be expressed either as a rectangular coordinates by spacing s lambda, and the circumference is c lambda, and the polar coordinates by the length of one turn l lambda, and pitch angle will be alpha. So spacing is spacing, if when the spacing is 0, then you can say that alpha is equal to 0 and the helix becomes a loop. Okay, and when the on when the diameter is 0, alpha will become 90 degree, and you can say that the helix become a linear conductor. So these are the things which we discussed in the previous class. Continuation of that. So continuation of that we will be seeing further. So we have some mode of operation, that is the transmission mode. So what can it be called as transmission mode? And it describes the manner in which the electromagnetic waves propagate along an infinite helix, and as though the helix contributes an infinite transmission line or waveguide. So that you have a transmission mode T, and then you have a radiation mode R mode of operation. It describes the general form of far field pattern of a finite helical antenna, and you can say that though there are possibility of many R modes, but the following two modes have been of higher significance. Okay, so this is what we have. We can see that you have a transmission T mode as well as a radiation R mode. So this radiation mode and transmission mode are required in order to find the electromagnetic wave propagates along a infinite helix, and also in the far field pattern of a finite helical antenna, the possibility of many R modes, but the following two modes are of higher significance. Okay, so uh, so you can just note down these things: transmission mode and radiation mode. We'll be further discussing. So you can make a note of these things, and then further, as we know that there are two R modes, but the following two modes are of higher significance. That is a normal or omni mode. So that is the one, and the other one is axial or beam mode. So If you take a normal or omni mode, the radiation is denoted as R0, in which the radiation beam is perpendicular to the helix axis. So here it is perpendicular to the helix axis. So that is called as the normal or omni mode, and in the case of axial or beam mode of radiation is denoted by R1, in which the radiation beam is parallel to the helix axis. So one, it is perpendicular to the helix axis, that is called as a normal or omni mode, and the R1, in which the radiation beam, the radiation is denoted as R1, in which the radiation beam which is parallel to the helix axis, you call it as a beam mode or axial mode. So these are, see, along with this one, that is transmission mode and radiation mode, the R modes can be further classified as two modes, have higher significance, what you can say, and they are these two. One is called as a normal or omni mode, and another is called as a axial or beam mode. So you can just make a note of these things, and then we'll continue further. In a normal or omni mode, you can say that the radiation beam is perpendicular to the helix axis, and in the case of axial or beam mode, you can say that it is parallel to the helix axis. So you can note down these things. So, the normal mode and axial mode we have understood. Further, we will discuss upon the practical design considerations for a axial mode of helical antenna. So, what are the things which you have to consider? You have see, I have told you before also when we were discussing the module 3, where we have seen different parameters of an antenna, where you have seen the beam area, beam efficiency, directivity, gain, aperture, all those things, as well as beam width, then all these parameters you have learned, and those parameters are required for any of the antennas whichever you are going to design. And when you design an antenna, you have to calculate all these parameters. How is the radiation resistance, whether is all the parameters optimum, or any of the parameters are shooting up unnecessary. So you have to change the design as per the required process, and you have to make sure that your antenna has an optimum way of transmitting and receiving the signals, and it is able to give a better efficiency at the time of design process as well. So we have also calculated there the gain, how to calculate the gain, and also to find out the directivity. We have also seen in that portion the beam area, beam solid angle, as well as the pattern, radiation pattern, how the radiation pattern will be, how the what is the significance of a main lobe, side lobe, back lobe, and all those things we have seen. So similar to that, all those parameters what we have studied is applicable for each and every antenna whatever you design. So when you take the HFSS is the tool used for design of any microwave devices or antenna setup. So what you can do is there you can see that how the pattern gets generated, or you can have a entire real-time design process, and you can check that how the gain, bandwidth and all. Then you have to, after your process is finalized, then you go for the manufacturing of the antenna in the real-time scenario. So as per the requirement of the user, so the user has to define all the parameters and make sure that the antenna works as per the requirement of the application. Okay, so when we look into the practical design considerations of a axial mode helical antenna, you can see that the important parameters are beam width, gain, impedance, and axial ratio. So, so all these things are very much important, like beam width, gain, impedance, and axial ratio. So, you have to keep a note of these parameters, and we can have specific equations in order to calculate these parameters. So you can calculate the beam width, and you can also calculate the gain of an antenna, and impedance and axial ratio. So all these parameters can be calculated as part of the design process. So that's what we have discussed about helical antenna. You can this I have given you a complete overview of that. You can just go through the textbook and add on few more equations and few theory concepts also when you put it in the answer paper. Okay, so the other one, the other antenna, the next antenna, that is called as the Yagi-Uda antenna. And here, this antenna, the main application of this antenna is this is a different antenna. So helical antenna we have already seen. This is the next antenna, that is called as Yagi-Uda antenna. So in Yagi-Uda array, you can call our Yagi-Uda antenna. So where this antenna you might have observed in your it's a quite common antenna which you can see in most of the cases where you have a TV transmission where you receive the signal for television. So you might have seen that on top of the terrace you may be using this type of antenna with lot of strips. So nowadays it is not quite common because of the dish antenna. Before the most of the TV applications and all, so we were using the Yagi-Uda antenna. Here you can say that it's classified into three, like reflector, then you have a driven element, and you have directors. So there is some significant length and variations which has to be maintained. So you have to see that the directors, these are, it can be more number of directors. So these are the directors. These are strips of, you might have seen that in your home. It may, when you are in childhood days and all, it was quite common that the most of the antenna almost 15 years back in our country, it was the Yagi antenna only which has been used for the TV, and you can see that on top of terrace this kind of antenna will be there. So here this antenna is having three different classifications, you can say. It has a reflector, and it has a driven element, and it has directors. So you can have more number of directors as well. There is it's okay for that. And here some major important things what you have to understand here is the driven element is the point at which the signal can be fed in. So this is the place at which this is called as the driven element, and between these two the spacing is very important. So you can see that 0.25 lambda, and here it is 0.31 lambda process completely. Okay, and this thickness of this metal, you can see here, it is 0.01 lambda. So you have to have a proper measurement for that, and for this thickness also it is 0.01 lambda. And so you can also see that the length, this is the length of the reflector, and length of the driven element, as well as length of the directors. You can see that there is a variation. So the length is 0.475, 0.46, and so on. So the modern version is a 6-element Yagi-Uda antenna, which so nowadays these things can also be seen in villages also, because in see this technology has been overruled by the dish antenna, which nowadays you can see most of them in TV reception. You can see that we are using either cable, or we are going with the dish setup. So you might have seen that you have all the dish antennas being placed. It can be Reliance or Sun Direct, or anything, Tata Sky, anything. All these things has come out with a dish antenna, and you might have also seen that as and when the variation. So you slightly change the antenna setup from the line of sight propagation. So you can see that the entire signal gets disturbed. Okay. So those things also you might have observed, and you can see that when some disturbance like rain or something is there, you will not get the signal properly. So that is some of the applications of that. The entire length, you have to say that it will be from the reflector to the director, it will be 1.5 lambda, and this is what you are going to have the shape of a Yagi antenna. So here when you do the calculation for the directivity, you can say that the maximum directivity is 12 dB, and at the center of the band, and bandwidth of 10% of half power. So these are the some specifications you can say. Now moving on further, a typical modern version of 6-element Yagi antenna is which we have seen here. It consists of, as I have told you, it has driven elements, and that is folded lambda by 2 dipole fed at a 302 wire transmission line and twin line, and a reflector and 4 directors are also available. So you can see, you might have already observed those things. So you might have observed those things, that you have directors and reflectors and driven elements. So you can just draw this diagram for a minute. I'll get back to you. So you can make a note of those things, and then we will proceed further. So here the main thing is that reflectors, driven element, as well as the directors, and you can see that its length will be varying. The length of the reflector will be slightly more compared to the rest of the things. So all those things you should be careful when you are designing it. So there are some specific, there you have to be specific when you are designing all those things. As we have seen, you have a driven element, you have a director and a reflector. So you have driven element, reflector, and 4 directors. Okay, you have observed those things in the figure. Now, when we move on further, the dimensions, as I have told you, length and spacing is very important. Indicated as in figure. You might have also observed those things. The length of the spacing between the driven element or a reflector, or between the directors, you have seen that. And when you talk about the length of the reflector, as I have told you, it will be slightly more compared to the driven elements or directors. So so those things we have to be very much careful. And the antenna provides a gain of 10 dB and that is the maximum, with a bandwidth at half power of 10%, and by adjusting the lengths and spacing approximately, and the dimensions can be optimized, producing an increase in gain of another decibel. So that is what it can also be. I have been saying you that we can optimize the process by changing the parameters slightly, and you can see that how best your design process happens when you are completely designing the antenna. So the dimensions can be optimized and producing an increase in gain and of other decibels. So if you want to increase the gain, that is also possible by changing the dimensions as and when required. So based on the applications, you can do that. So that is all about Yagi antenna. So you can just go through those things. Different types of antennas are there. Some of one or two I will be taking extra beyond the syllabus as well. So you can just see that you have Yagi antenna, you have helical antenna, and all those things. So you have another type of antenna that is called as parabola or parabolic antenna or parabolic reflectors. So here the shape it's of this type where you have a sheet reflector and you have the plane waveform. Okay, 1 second. So we are now going to discuss upon the parabola general properties or parabolic reflectors. So you can see that the shape of the parabolic reflector will be in this kind. So what you can see here is you will be having a sheet reflector, and then you have a focus point that is denoted as F, and this is L, and this angle which gets generated at this path of signal, that is called as theta, and this is the R, and the path 1 you can say, and the other one you can call it as path 2. So this is what it happens here. You can say that the parabola, the shape, it is in this form, and the signal has a focus. This parabola will have a focus point as well, and you have a vertex, and the axes are also available. So the signal, when it hits on the sheet of reflector, it also focuses on the focus point, and you get the you can see that the transmission and reception of the signals will be carried out in this way. This is the aperture plane, and where you can see here where the uh, all the points have been denoted. So we will just discuss these things. So here we have few equations to understand. It is required that the distance from the source to the plane wavefront, that is path 1 and 2, you can say 2L is equal to R into 1 plus cos theta when you take it from this figure. So you can say that L, so this is L, so you can from this you can write with respect to cos theta, so you can say that 2L is equal to 2L is equal to R into 1 plus cos theta. So from this R you can find out. So from this, when you take out R will be equal to 2L divided by 1 plus cos theta. So here if you want to find out R, you can use the equation 2L by 1 plus cos theta, and the parabolic curve, as I have told you, the parabolic curve may be defined as follows: the distance from the any point P is the this point you can see here. P is this point. So you can see that the distance from any point P on the parabolic curve to a fixed point F called the focus is equal to the perpendicular distance to a fixed line, which is called the directrix. Okay, so you can from this you can also write from the figure, you can see PF is equal to PQ. So that and all you can observe here. You have the points PQ, you have the points P, Q and F, all those things. So you can write that from this we can also write that F is equal to PQ, and as well as we can write from the figure that PF plus PS is equal to PF plus QS plus minus PQ is equal to QS. So these are some of the equations in order to calculate the parameters which is relevant for the parabolic antenna. So what in brief you can say is the shape of the antenna is in the parabolic nature, and you have a focal point, and as per the requirement you can design the antenna parameters, and all those calculations can be carried out. Okay, so these are some of the equations for you can make a note of these equations. So you can just note down these equations. For R, it is 2L divided by 1 plus cos theta, and this PF is equal to PQ, and so all these things can be changed according to the requirement. So you can vary the focal point, you can adjust all those things. So it's how when you design the antenna, you have to keep a note of all those things. So you can just note down these points, and then we will go further. So further we will discuss on one more antenna. Further we will discuss on one more antenna, that is called as log periodic antenna. So this is another antenna. In this some of the antennas I am just teaching you, that is not there in syllabus maybe, but we are just discussing that. So this is the last antenna which I am going to discuss. So that is called as log periodic antenna. So here you have this is the shape of the antenna, how it will look like. So this antenna is called as the log periodic antenna, where you have a element where you feed in, and you have inactive, that is the transmission line region where L is less than lambda by 2, and you have an active region where L is equal to lambda by 2, and you have an inactive region or where L should be greater than lambda by 2. So that is how it is classified into the log periodic dipole array, and you can see that. So this is the inactive portion, and this is the active radiating region, or this is the inactive transmission line region, and where the signal is fed in or it is received back. Okay, so this is the active region where L is equal to lambda by 2, and when L is equal to lambda by 2, you can say that the radiating region. So either the signals are radiated or it is received back. So this is called as the inactive region, where L should be greater than lambda by 2. So here L is what? This is, you can see here this angle. Now you are going in this direction. These two means this angle which is getting generated is called as 2 alpha. This all things are required, and then the distance between these two, it is Sn, and here further it will be Sn plus 1, Sn plus 2, etc. It will go on. So here it is Ln, and this one, and it will be Ln plus 1, etc. So this pattern of antenna, it is called as the log periodic antenna or a log periodic dipole array. So here referring to the figure, the dipole length increases along the antenna, and so it include the angle alpha, as I have told you, as we have seen in the figure, is a constant. So the angle alpha is a constant. Here it is given 2 alpha. So this is the angle. So it will be a constant, and you have certain design parameters which you have to consider. You cannot simply do it. You have to keep it in your mind, how the length of the antenna has to be, how the spacing has to be, everything has to be defined properly. So when you go ahead with that, you can say that angle alpha is a constant, and the length L and spacing is S of the adjacent elements are scaled, so that Ln plus 1 divided by Ln is equal to Sn plus 1 divided by Sn, that is equal to K, where K is a constant. So this is what you can observe here. So you can make a note of this equation. Ln plus 1 divided by Ln is equal to Sn plus 1 divided by Sn is equal to K, and L is the length, as I have told you, and S is the spacing. So you might have observed in the figure already. Where K is a constant. So let me just draw this figure. I have just taken a geometry. So I have just taken a log periodic array geometry for determining the radiation parameters. Same thing, same figure. I have just taken a small portion of that, the same figure. So I have taken only this part. You can see that this portion I have used here for the calculations. So you can see that half of the portion, so this is, instead of 2 alpha, you can see it is alpha, and this side I have not taken. Okay, you can see I have taken only half of that. So like this portion only I have taken. So when you take that, you can see that it is alpha, and this length, it is Ln, so it will be Ln by 2. This length, it is Ln plus 1, so it is Ln plus 1 by 2. So this angle is also alpha, and the spacing is S. So here this small length, it will be Ln plus 1 minus Ln divided by 2. By using these things, we can just do some calculations. You can make a note of these things: log periodic array geometry for determining the relation of parameters. So you have to understand the significance of each parameter, and you should take care all those things at the time of design process. So this is what the figure, you can just make a note of it, and then I will proceed further. So moving on further, when you use the figure, you can say that tan of alpha can be written as, you know that it can be written as tan alpha here. So I can write tan alpha. I am using tan alpha here. This alpha, tan alpha, can be written as Ln plus 1 minus Ln divided by 2 and divided by S. So S is the spacing. So from equation 3, we can say that alpha, tan alpha is this, you can write it 1 minus 1 by K into Ln plus 2 divided by Ln plus 1 divided by 2 divided by S. Taking Ln plus 1 is equal to lambda by 2, when active, we can say that tan alpha is equal to, simplification I am doing, that's all. So tan alpha is equal to 1 minus 1 by K divided by 4 into S lambda. So when you are taking Ln plus 1 is lambda by 2, that is when active, in the active region. So you can say that Ln plus 1, I am replacing it by lambda by 2. So lambda by 2 will become lambda by 2 divided by 2. So lambda by 4 it will come. So when you consider that, that's why we have written it as S lambda. Okay, so it is in terms of lambda. So S tan of alpha will be 1 minus 1 by k divided by 4 S lambda. So alpha is called as the apex angle and k is called as a scale factor, and S of lambda spacing of wavelength shortward of lambda by 2 elements. So S of lambda indicates the spacing in wavelength of lambda by 2 elements. So that is what you can see here. So these are some of the equations what you get in finding out the parameters of a log periodic array geometry. So you can these are some of the very important concepts which you have to understand. So this is all about the different types of antennas we have discussed on helical antenna, horn antenna, Yagi antenna, and parabolic antenna, as well as log periodic antenna. So, so that's all for this entire antenna and wave propagation and microwave and antenna syllabus. So we have covered all the concepts, whatever it is required for you in this semester. Okay. So that's all for today. We can, if you have any doubts, you can discuss. Otherwise, we will wind up for today. So you have to do one thing. I have already given the entire syllabus is completed. I can say that 100% syllabus is done. And when you have any doubts, you can feel free to discuss with me. So this is all about the microwaves and antennas for this sixth semester, and we have covered up everything. Okay. So anything to be discussed? Is that clear for all of you? Is that clear for all of you?
Yes, sir.
Okay. Okay, then other than that, you can just refer the textbooks also.